as usual, let's have a little resume of what we have seen in the last lecture, which is the following. So we found out that the compaction function can be written in terms of a quadratic form of this, what we would call linear over density, which depends on the smoothed linear over density, which depends on the smoothing radius r, and depends on the center where this large peak is centered, okay, which is called x con 0. And so this is a quadratic form, so it's 1 minus 3 divided by 8 g r of x con 0. Okay, so we found that. And we also found out that, well, we define type 1 black holes, those who has a critical threshold such that g r x con 0 critical is less than 4/3. Okay, so we will just focus on those. And so in that case, all the properties of C are immediately going to the properties of G, meaning if I take any derivative and I want to put the derivative equal to 0 for C, is it the same if I do it in G? And if I want to have the second derivative to be less than 0 in a peak, is the same as second derivative of G being less than 0 in a peak. Okay, so that because a peak is a maximum. Okay. So for a large value, for example, or for any variable, okay, for r and for x con 0, okay, if we are in type 1 black hole. So basically we can focus on G rather than focusing on C. Now, the second thing that we found is that, as we say, at the threshold, the mass of the black hole is 0. So threshold means forming a black hole of mass 0, as weird as it could be, okay, but it is like that. And for this reason, the mass of the black hole, this is the numerical input, follow a self-similar solution, which is a constant, which is order 1, and which is weakly dependent on the shape of our compaction function over density, divided by 2 times the Hubble scale when the maximum of the compaction function crosses the horizon, we'll define now, multiplied by the compaction function at the maximum, minus the compaction function critical to the power 0.36. Okay, so this is the mass of the black hole. So the mass of the black hole is not all the mass that the horizon have when this perturbation entered the horizon, but is only a fraction of it. Okay, it depends on how large was our perturbation.
So what physically distinguishes the type 1 and the type 2 black holes?
Well, it's precisely this, that when we increase the linear over density for type 2 black hole, if you want, the gravitational potential decreases. But this is just it's just a mathematical thing, because actually the linear over density is not the nonlinear over density. The nonlinear over density is the full sum, and this full sum is on growing. Well, it's
and do we have a feel for whether
it's decreasing
black holes
actually.
that are formed will be of one type or the other type?
What do you mean we have a feeling? Well, type 2 black hole. Okay, so type 2 black hole, I don't want to enter into this, but type 2 black hole can form either a black hole or a separate universe. So it's a complicated thing, and if you are in type 2 black hole, actually it seems that there is no threshold. I mean, any perturbation will kind of collapse. And but this is also not completely true, because there are some gray zone region where you have a little bit over threshold type 1, which you form or not form black hole, because it changed completely the physics in that case. And but people don't really yet know exactly what is going on in type 2. So it's an open research. This, I mean, there are some simulations. So far people have done some simulation with specific profile for type 2, and some different weird thing happen, is that in type 2, what happens is the following, that so while in type 1 you form, so this is a trapped horizon, but there is always, in type 1, there is always a kind of cosmological horizon inside. So the black hole is always formed and it's up the cosmological horizon. In type 2, there are some regions in which the cosmological horizon overcomes the trapped horizon. So you form a kind of separate universe in the sense that there is a cosmological horizon outside, and then there is kind of a formation of black hole trapped inside this horizon.
The cosmological horizon is essentially H inverse.
Yeah, correct. Yes. Okay. So, but as I said, we are not going to go there because in any case, I mean, you need an extremely large value of G to form this type 2. So we're going to see that statistically it's very improbable because the probability distribution of G is Gaussian, so it's exponentially increasing, and so larger value of G, it's more unlikely. Although, I mean, you can have those, but yeah, that will not give you let's say the most of the abundance of the black holes. Okay. So what is HRM? As I said, is H at the scale Rm, which is defined as a crossing horizon scale when the scale Rm is equal to the physical scale, which is the scale factor multiplied by Rm, is equal to the Hubble horizon, okay, the Hubble radius, okay? And because we are in radiation, H is equal to H at equality divided by A squared if we are using A at the equality equal to 1, okay? And with that, I mean, you simply invert this and you find that HRM is actually equal to 1 over H equality Rm squared. Okay? So note that, well, so then the mass of the black hole, we can better write now in the variable that we have, which is Rm, and well, the value of C or G if you want. Okay, so this will be K divided by 2. There will be H equality Rm squared of C. Let me write G of Rm of x con 0 minus C critical 0.36. Okay, so this is the mass of the black hole, which you can see that larger as it should be. No, the larger is the volume. Perturbation re-enter the horizon, larger is the black hole mass because we simply have more space to fill up.
So where did we make that assumption that it has entered the Hubble radius, re-entered the horizon?
We didn't. So we are talking about super horizon scales. Okay, so perhaps I didn't say that. We're talking about super horizon scale, and this sets the initial condition of our simulation, let's say. So we simply let it evolve. Of course, what I say is that it doesn't evolve a super horizon scale, but I mean, it's a leading order, let's say, because as usual, curvature perturbation are almost constant. So we have to wait a little bit, and then at some point, the perturbation, of course, re-enter the horizon. Once re-enter the horizon, the full nonlinearity, so gradient expansion is not valid anymore, and the full nonlinearity of general relativity should be used. And you cannot do it by hand now. So you really have to use your computer and simulations. And so you will see, then in certain case you will form a black hole, in other case you will dissipate away. Okay? And the threshold is precisely the moment in which, as I said, you will almost form a black hole. Okay? But you have to re-enter the horizon for causality condition, because super horizon scale is all frozen. So in order to evolve to something that is of order 1 of the compaction function, you need to evolve. You need to re-enter the horizon. Okay. And So interestingly also, let's suppose I associate, even if I should not really do that, but let me suppose I associate a wavelength to, a wave number to the inverse of the maximal radius. As we see, the mass of the black hole is inversely proportional to the wave number square. Okay, so well, it's the same message. If we have a very long wavelength, then or a very short wave number, then we have a larger mass. Okay, so it's kind of the opposite somehow, that something they could think of.
And somewhere this relation assumes it is radiation domination.
This relation assumes that it's a radiation domination. If it is not, so first of all, it's not clear whether we have self-similar scaling for the mass. If we have, in certain cases we have, if we are close enough to radiation. Of course, for example, for dust we don't have, because everything collapses. So, but close to radiation we do, and but the critical exponent will change, so it will not be 0.36. And what else?
Because even in the
Well,
standard
this.
formalism,
Yes.
you will get some relation like that, if I recall correctly.
Which one? This one.
The M-K relation.
Okay, so in standard press shatter, what you'll get, I don't know what you call standard press shatter, but let me suppose I know. so the standard press shatter would say that the mass of the black hole is this. If I understand what standard press shatter is for you, so it's. But as you can see, this would mean that basically any value of the compaction function, as long as, so if you want, actually it's something like this, it's multiplied by this, multiplied by some threshold. Okay. So as you can see, I mean, of course the scaling is completely different, because this is like a power law, and on the different here is just a cutoff. Okay, so, but standard press shatter also doesn't define what is this. So I'm giving a precise definition of what is a threshold.
So just one more
question.
When you say R maximum, you are thinking of a situation where the mass is accreting, it's growing and turning around and collapsing. Is that what you have in mind?
No, R maximum is the maximum value of the compaction function at super horizon scales. Yes. So is this? It has a maximum, and so is the largest value of the gravitational potential, because the compaction function is almost constant until crossing the horizon. It's still gonna be more or less the maximum value. So you can imagine this would be the value you should give to know whether at least this little shell will collapse. Okay. Right. Okay. So now, so in principle, what you should do. So now we have to find precisely this value here. Okay. So that's the question we have, and this value there. So if you can use your software, as I said, and plug it there and do simulation, which are kind of simpler than the full general relativity simulation if you are type 1. But in fact, if you are type 2, now if we want to go back, it is not such simple thing, because if you use spherical symmetry, so if you really use the metric that I wrote it always, which is diagonal and so forth so on, you will find that there is a coordinate singularity precisely at the moment in which you go from type 1 to type 2. Okay, so people actually didn't know how to do this simulation until not even 1 year ago. Okay, so, and they use what is called, I mean, I'm not an expert, but it's called BMSSM, or I don't know, some name for using special coordinates that basically remove this this coordinate singularity, I can integrate the equation all the way through, okay, without passing through this cosmological this coordinate singularity. You know the name of it? BSSM. Yes, BSSM. Okay. BSSN. Okay, sorry. Okay, you know better than me. So in this way, basically, you don't have the problem of passing through type 1 and type 2. So people wrote down a new code, and then basically, so they could get this simulation done for type 2 black holes. But as you understand, it's something that is done not even 1 year ago. So imagine that a lot has to be understood. Okay, while simulation on type 1 black hole goes back 20 years and more. Okay. But the problem of simulating type 2 was simply that. It was simply that there was a coordinate singularity, and with the coordinate that you would use in the Misner-Sharp-Hernandez system, you get some nonsensical result precisely because you have this coordinate singularity. Okay, so you have to use more sophisticated gauge to solve this problem. All right. Okay. So. Okay, so now what we want to find, as we said, is this critical value of the compaction function. And as I said, I mean, if you do the simulation, what happens is that, so this was the guy that did for all his life all this simulation was Musco. So there are several papers of him. You can see in the archive. I mean, he's always doing these things. So he actually showed in 2019 that this threshold actually depends on this full shape of the compaction function. So it really, so if you modify this shape here, then you will get another threshold. Okay, which kind of makes sense because it depends on the gravitational potential in each shell. Okay, so then this is basically differing a lot from previous ideas of thresholds because, for example, we mentioned yesterday the Japanese. So what happens there is that there was no shape dependence. So they were saying that the threshold was kind of universal and depend only on the equational state. This is false because numerically you can see this is false. And there was also the earlier threshold was given by Bernard Carr, that was saying basically was using G's instability to get gravitational collapse and was saying that basically everything was related to the sound speed, and the sound speed only depends on the equational state. So it's again is a universal number. But what we learn from numerical relativity, okay, is that there is no universal number for threshold. Okay, so it doesn't only depend on the equational state, but actually depends on your initial condition, the full initial condition.
The full power spectrum.
We will get to the power spectrum, but for now we are not connecting to the power spectrums yet. Okay, but of course, then after will depend on the power spectrum. Now, but now let's think a little bit more about what the threshold again means. Okay, so the threshold, and this is what we have done in this paper. When was it? I don't know. Well, was I told you yes, now I forgot. It's probably, I don't remember. Huh? 2020. Okay. Okay. Yes, it was just after this. So we noticed the following. So we rethought about what a threshold is. Okay. So a threshold, because as I said, I mean, if we have to do, imagine here is a random generation of perturbations. Okay. So we have infinite profiles that are generated. Okay. If for each profile I have to do a simulation to get a threshold, that's it. Okay. We cannot do anything. So we really need a way which would approximate our threshold, numerical threshold, but that relies only on analytical calculations. Otherwise, we just simply cannot do anything, okay, statistically. Of course, if you have supercomputer that runs, I don't know, years, maybe you will get the same result, maybe, okay? All right, so the threshold. So first of all, we have some conditions that we already say that C has to go to 0 for R going to 0 and also for R going to infinity. Okay, so this is the physical condition that at the center the gravitational potential is 0 and also at infinity. Okay. All right. So now, in fact, one finds from gradient expansion that the compaction function goes to 0 like R squared. Okay. Now, second thing, the threshold, as we said, is the value of this parameter such that we form a black hole of mass 0. So black hole of mass 0 would mean that there is only a very thin shell that is collapsing and everything else not. And because this thin shell is not infinity, it will give you mass 0. Okay, so right, so it's like a shell of width very small. So then it will simply give you, we can think that way, it will give you a mass equal to 0. So then you can imagine that the whole physics for the threshold, not for a black hole with mass different from 0, but all the physics is around the peak. Okay, because we are thinking about a shell, a very small shell that is collapsing. Okay, so then if I have a compaction function that has 0, it goes like R squared here, and here goes to 0 at infinity. What I'm interested in is actually only what happens around the maximum, okay, for the threshold, okay, because I'm generating a mass 0, so I don't care what happens more than around the maximum, because anything else will dissipate away, okay. So the idea we had is that actually, instead of using the full compaction function, so it will be the full shape, we actually take a base of function that approximate the compaction function around the maximum, like a Taylor expansion around the maximum, so it will depend only on the second derivative, so the curvature of the compaction function, and this base have to have the physical condition that approach to 0 like R squared. Okay. Now, so for reasons that are going to be clearer later on, instead of using the coordinate R, okay, let me use the area radius coordinate. Okay, almost, because I'm removing the scale factor. So let me use R tilde, which is simply e to the zeta R. Of course, I can always invert. Okay, so this R in terms of, okay, so I use this. Why I say it's almost the area radius? Because of course the area radius will be R tilde multiplied by A. Okay, so I'm removing the scale factor. So I'm just taking the constant part. Okay. And so then we approximated this function as a family of Gaussian type profile. Okay, so the choice we have made, by which we check that you can take actually any base you want, and you will get roughly the same result. The compaction function fit that we used, it's equal to this R tilde squared divided by R tilde m squared. R tilde m squared means R tilde when R is equal to Rm, of course, okay? And then e to the 1q, 1 minus R tilde over R tilde m to the 2q. So you can check that, well, this kind of profile you can put in your Mathematica. It looks like more or less a a Gaussian around the. Well, it's not really a Gaussian because it terminates in R square, but it's around that value. It looks like a Gaussian, okay, with certain curvature. Now Q, of course, the only parameter that is interesting once I tell you that I'm only interested on the peak is the peak value, okay, and the sorry, I miss here, of course, C at the peak. Okay, is the peak value and the curvature. Okay, so this Q parameter obviously is going to be related to the curvature, and it is actually minus, is a normalized curvature because we want to have a dimensionless quantity. So now this second, so let me write perhaps this C square d tilde square at Rm tilde over 4 times C R tilde M. Now this 4, it's simply for historical reason because these kind of profiles were used in the simulation of Musco, and we are simply using the same thing. So that's, so the idea is that we actually use those profiles as a fit for whatever compaction function. Okay. So the only thing that we will need now it's the curvature, so the derivative of the compaction function around Rm, and of course its value, okay, which is the critical value. Now, well, not the critical value. For now, it's just the value at Rm. Okay, but that's our fit. So now the point that we made. So until now, is just we say, well, the physics only depends on the maximum, but still we have to know the threshold. Okay. And so what we did is the following thing. So we say that, well, if the physics only depends on the maximum, then let me do something different. Let me actually consider, instead of this compaction function, let me consider the compaction function which is the average of this. Okay, so I average out the compaction function, okay, and this is equal to 3 times, so spherical symmetry, R tilde to the cube, M, then is a theta function, R tilde minus R tilde M, and then I integrate over 0 to R tilde M, C fit of R tilde prime, prime means another variable, okay, so R tilde prime square d R prime tilde. So prime is not the derivative here, it's another variable. Perhaps I should write, well, whatever, bar. Bar. Yeah. Okay. Okay, so then now because we are all interested in the physics around the peak, so what we said is that, well, instead of taking the full distribution, I actually average out, and I just consider the average of this thing. Now, yeah, we need to have the input of numerical relativity. This is a compaction function that is a theta function. Okay, so the question is, what is the threshold for a theta function compaction function? And the threshold for a theta function compaction function is 2 divided by 5. It's a straight number. Okay, so now, as you see, I erase all the information at this level of the shape of our compaction function. So the idea is the following. So I know that the threshold for the mean value is 2/5. So how do I get the threshold for actually my compaction function, which is not the average one? Well, I simply invert this integral. Okay, so that's the idea. And then what you get, so you basically plug this into the integral, you do your integral is gamma function, whatever it is, okay? And then you simply invert for this value here, which is the value of the peak, okay? So the threshold then turns out to be, by construction, only dependent on the on the second derivative, and the value of Rm, of course. Okay, so we define then the compaction function, the critical compaction function threshold that depends on Q, and Q depends on, as we see here, right? Depends on Rm and the second derivative, so the normalized second derivative. And this guy is the following: 4 divided by 15. I just write you because it's interesting to see that it's an analytical formula. 5 divided by 2q divided by gammas of 5 divided by 2q minus gamma of 5 divided by 2q 1 over q. Okay. So now, what you do, you now check that all we said makes sense. Okay. So what you do, you take the threshold that you would get. So you understand, if I have a profile, I can just get the Q because it's the curvature at the maximum. The maximum, I put it in some point R, and then I get a threshold. What you find, you take this, you plug it, you put it in your code, and you check whether the threshold is correct, and this threshold, amazingly, matches the numerical result up to 2% error. Okay? Which is just enough for all the statistics we want to do. Okay? So this is the point in which we can actually now do statistics. Okay? Because now we know analytically we can put into our statistic, we can put the value of the threshold, so to know when I would form a black hole. Okay? So this is a crucial step.
So there is something I'm not able to understand. So what value of Q am I going to work with?
This will be statistically produced. So you will have different Qs. So your statistic will generate different profiles, which we are going to see. Okay? Your statistic will generate different profiles, and so for each profile you will have a threshold.
The statistics
of the compaction function. Or the statistic of zeta, if you want, because at the end everything is related to zeta, which we're going to see in a second, okay? But the key point is that you have to imagine that statistically we produce all randomly generated profile. Each one of those will have a threshold, okay, as a profile without the rescaling. So then will be a statistic of the rescaling, okay? Right. Okay, so the first part of the statistics, so now we really go into the statistics. So for now, this was just classical general relativity, okay? So I give you some profile for the overdensity, which you can give me back a profile, I mean, you can transform immediately or into a profile of compaction function, or a profile of curvature, and you can give me back the profile of compaction function, and I told you which one is the threshold, the value that you have to give me for this profile in such a way that I would form a black hole. Okay? So that's where we are now.
Can I just briefly summarize for my own benefit? In the sense of, you started with essentially the Einstein's equation to determine the relation between your zeta and the energy over densities.
Correct.
That's where we started. Okay.
Correct.
And then you use the scaling relation to determine when something will form a black hole. Am I correct?
No, the scaling relation is the mass of the black hole. What you want to know, so the mass of the black hole is the ending state of your numerical evolution. But what you want to know is what is the value, the condition to start forming a black hole.
Okay.
Yes.
And that's where the compaction.
That's where the compaction function comes in. And it enters also on the final mass, because the final mass is related to the compaction function value. Yeah? Okay.
And again,
Yes.
The mass is only to determine the mass, you have used that scaling relation, the Chopin scale.
Correct.
And if it collapses in other than a radiation-dominated universe, I just need to relook at that scaling relation, and all the other arguments will go through.
Well, yes and not, because, for example, we have done the same study for the critical value, in cases of different equational state. Okay. So what is happening is the following. You know, I mean, you can already understand that, for example, for dust, this condition makes no sense because dust, any shell collapses. Okay, so you just have to give me enough time. So the question of dust is, do I have enough time to form a black hole or not? Okay. But for radiation instead, things are different because for radiation you have the pressure that is also fighting the collapse. And then it helps at some point when you form traps horizon. So you can imagine that the physics is quite different. And in fact, it so happened that what we show is that if you are close enough or you are steeper than radiation as equational state, then you can still find a threshold analytically, okay, in terms of the compaction function, no problem, still with a very good percentage, okay? But if you start going with an equational state less than radiation, in fact, radiation is a kind of the threshold in terms of equational state. If you go lower, then it just doesn't make any more sense to even talk about compaction function because it's not gonna be the maximum of the compaction function that is gonna collapse first, but in fact the one that is closer to the center. Okay, so radiation is the moment in which the thing goes the other way around because everything wants to expand. Okay, so it's tricky if you're not in radiation. But if you're not in radiation, also other thing changes. For example, if you form the black holes that are not in radiation-dominated universe, you have to be very careful because you will not have anymore this ratio between density of black hole and density of radiation. So you will have always that those can be of order 1. So you may over-dominate the universe. So the fact that they are formed in radiation, I think it's a very interesting thing because we know that radiation happens in our universe, and because we have this idea that I need only to form few of those, so it's naturally related to inflation. Other scenarios would be more tricky. Okay. Okay. So all right. So far we have this. So now we can check. Actually, now because it will be anyway part of the statistics. Until now, I convinced you with words that large fluctuations are spherical. Okay. So let me now prove statistically that this is true. Okay, so if I have a large fluctuation, this is very close to be spherical. So what does classical fluctuation means? Large fluctuations mean? It means that the value of this GR that define the compaction function over its 2-point correlation function, square root, its variance, it's much bigger than 1. What do I mean with this? So what we said is that you probably have forgotten by now, but the GRx con 0, it was an integral over a ball centered in a point x con 0, okay, and with radius r, of the Laplacian of zeta. Okay, this is how we constructed this G, okay. So, because zeta is a statistical variable, okay, this is simply the integral of the Laplacian is still a statistical variable. It's still the same statistical, well, it's not the same statistical variable, but it's still Gaussian. So if one is Gaussian, the other one is Gaussian. The only thing that will change, of course, the correlator will know that we are doing an integral and a Laplacian. Okay. Okay, so as we said, we can focus. Although we want to have, if you want, a peak in the nonlinear over density, which is the compaction function, is the integral of the compaction function. As we said, it's a completely equivalent for type 1 black hole to only look at G. Okay. So what we are going to have is we're going to search for a peak, so a large value of G. Okay, and see whether this is spherical. What does it mean is spherical here? Well, it means that if I take this point here in space and then I do a smoothing, okay, then if I move from this point and I take all the same smoothing, but from this other thing, they are all the same, because it's spherically symmetric. Okay, so if I move the point, x con 0, and another point, then it's gonna be all the same around the radius. Okay? All right, so what we want to see is whether moving this point, that is the peak, moving around, the geometry around this point is spherical. Okay, so this will mean that the peak is spherically symmetric. To do that, what we'll do, we'll use the celebrated peak theory. It was invented in 1986, which is often used in large-scale structures. So we are borrowing things from large-scale structures, and it was given by Bardeen, Bond, Kaiser, and Sanslai, also known as BBKS. Okay, so peak theory, also known as BBKS. Okay, so right. So then let's see what we want to do. So what we are interested is to know the geometry of a large peak around the peak. Right? Of course, if we go far away, then things can maybe be different. But what we are interested in is that if we have a large value of this g and is a peak, so it's a maximum, then whenever is a maximum around that and is a large maximum, this is spherical. Okay? So what variable we are interested in? Well, because we are thinking about going around the x con 0, so what we are thinking of, it's an expansion, a Taylor expansion of this plus the first derivative is 0 because it's a peak, okay? So then what we have is 1/2 di dj g r x calculated in x con 0 multiplied by xi minus x0 I xj minus x0 j, okay? Plus dot dot dot. So we are doing a Taylor expansion around the maximum, okay? So first of all, in order to know that there is a maximum, obviously what we need to have is that we need to impose that the gradient in x con 0 of g is equal to 0. Note that, I didn't put an R here, I should put. So note that we're focusing on its space position, okay? We are not focusing on the smoothing radius. So for now, for us, the smoothing radius is a constant. It's that we don't care, okay? We're just moving this ball around the space, okay? All right, so we need that this variable that we call it eta is equal to 0. And then, so this is given in x con 0, of course. And then we need that we define a new variable psi ij equal to di dj g x con 0. And what we want is that the principal direction, so this is the Hessian, okay? So the principal directions of these are all less than 0. You want to have a maximum, okay? So this we know from first year of undergraduate courses, okay? So what we want is a maximum. So in particular, for example, even nabla square of g has to be less than 0. The Laplacian has to be less than 0. So this one, but all the direction actually have to be equal to 0. So, so strictly speaking, what we have to do is to consider those variables, those statistical values. So our system become a multi-Gaussian distribution because each of those variables, as you can see, eta is the gradient of g. G was a Gaussian, so eta is a Gaussian. Psi ij is the Laplacian is the second derivative Hessian of g, so it's also a Gaussian distribution. Okay, so I can collect all of those in new Gaussian variable, multi-Gaussian variable, that is defined by G, eta I, and psi ij. Okay? So I have those. And of course, the condition that we want to put is eta I equal to 0 and psi ij to be negative. Okay? Right, because this is a Gaussian distribution, so we have that the PDF, the probability distribution function, is determined by the quadratic form, which is 1/2 sum over A and B. So A and B runs over all these index if you want. Okay, so 1, and then this is 3, and this 3 by 3. Okay, so this will be HA MAB minus 1 HB. This is the covariant matrix of the variances, which is nothing else than MAB equal to the 2-point correlation function of HA HB. And as you know, so then the probability distribution will be a normalization, which is simply the square root of the covariant matrix, e to the minus 1/2. The 1/2 I put it there, e to the minus q. Right? This is a Gaussian. It's a multi-variable Gaussian. So you have to imagine that we are in 1, 3, 4. 3 by 3, 9, 9, 4, 13, 14, right? Well, this is actually symmetric, so it's not, you have only 10 components actually. So this is 10, 13, what is it?
Just
Is it? Just spatial, yes. 3 by 6, sorry, 6, 10 in total. Sorry, I just, okay, because obviously psi ij is equal to psi ji. Okay, so this. Okay, so this also means, by the way, that I can diagonalize this psi. Okay, this is a symmetric matrix. Okay, so because we know the correlation function of zeta in Fourier space, then we better go in the correlation function. We better write this G also in Fourier space. Okay. Let me forget for a second, because it's simply just slightly more complicated to write down in terms of zeta, but I can always Fourier decompose G itself, okay? And this will be, of course, related to the Fourier decomposition of zeta. Okay? But at the moment, we don't care. Okay, so then GK, the Fourier modes, are gonna be the integral of G in x con 0 e to the minus k x con 0, and then d3, well, I should put an x, d3x. Okay, so this is simply the decomposition of my variable g. So what we are interested in is the 2-point correlation function gk prime, because what I need is this matrix. Okay, so this matrix is going to be the 2-point correlation function of all the g's and its derivative and Hessian. Okay, so this guy will be, of course, my definition as usual is 2 pi to the cube delta 3 k minus k prime, and then p power spectrum of g. Okay, pay attention that I'm using g because I want to complicate now the things, divided by k to the cube. The power spectrum of G, it's actually related very easily to the power spectrum of zeta for later convenience, which is power spectrum of zeta, W square, TH, KR, and then KR to the 4. Okay, but let me not carry on all these things. So let me just call it P of G. Okay. This is simply because the relation of G with zeta, okay, in Fourier space, that was involving this theta, the window function, if you want, multiplied by k to r to the 4, because it was a Laplacian square. Okay, so so now this is like in perturbation theory, and you know that if you have a scalar, so let me do a quadratic, so I want to do linear perturbation theory, for example. No? When I do linear perturbation theory, I have a scalar, vector, and tensor. Okay? How can they couple? Well, what we can have is that there are only few coupling that we can do, right? Simply because of index. So if we have a quadratic form, which is going to be kind of the Lagrangian of the system, the only possibility I have is that I get a G square, of course, right? Product itself. On eta, the only thing I can do is eta. Okay, eta is the first derivative. And then another possibility that I can have is, of course, G psi ij delta ij, so the trace of the Hessian. And then, of course, I can have the psi. Okay? Psi ij, psi ij. Okay? So this is the only possibilities I have of contracting the thing, and so to calculate the correlation functions. And well, we can actually calculate now. So if we define the sigmas j square equal to 1 over 2 pi to the cube integral of dk over k pg of k. So here is where all enters the power spectrum, as you can see. K to the 2j. So this is a definition simply. Okay. So then one finds that that we have this matrix mgg equal to sigma 0 square, and we have mf, why do I call it f? G psi ij, which means this interaction here, okay, equal to minus m psi, so let me put the index. This is equal to minus 1/3 sigma 1 square delta ij, okay, and then finally we have sorry, this is eta. Okay, and then finally we have m psi. Not that you have to remember now, but okay. So you can calculate this thing just to show you that there is a formula. So this delta ij, delta lm completely symmetrized. Okay, so those are all the variances that you have for this system. Okay. However, when you work on Gaussians, you better work on normalized variable. Okay, so basically you want to normalize your variance to 1. Okay, so you simply divide by the variance of the single variable. So instead of using, where is this? Instead of using g eta I psi ij, actually we are going to use the variable nu g divided by sigma 0. Okay, so then this new variable is variance 1. So you can see that unlucky case is when g over sigma 0 is much bigger than 1 because it's over the variance. Okay, when g is much larger than the variance. And then we use alpha I equal to eta I divided by sigma 1, and actually we define Cij equal to minus psi ij divided by sigma 2. I put a minus here because I want to have the eigenvalues positive, just because I don't like the negative thing. What time is it? Oui. Okay, so what do we do is the following. Now, as we said, we expand g of x con 0 around its peak. Okay, so this will depend only on the value of g at its peak. Okay, this g is the g of the peak. Okay, so here is the derivative and the second derivative. Okay, so what I'm gonna do, I'm not gonna show you because I have no time. But this is a Hessian matrix. The Hessian matrix is a 3x3 matrix, symmetric, so I can diagonalize. Okay, so if I diagonalize, I get 3 eigenvalues. Okay, and the whole matrix is defined by these 3 eigenvalues. Okay, so that's, And now g of x, it's equal to g of x0 plus 1/2 sum of psi ij, and then x minus x con 0 I and j, okay? This is a quadratic form, and in fact, it's the equation of an ellipsoid. Okay, so that's where we go to know the sphericity now. So then let me define, if I use now the eigenvalues, okay, I can define the sphericity parameters, which are E equal to lambda 1 minus lambda 3 divided by 2 sum of lambda i's. And then, so this is called ellipticity. And then there is the prolapse, which is equal to lambda 1 minus 2 lambda 2 plus lambda 3 divided by 2 sum of lambda i's. Now you can see that in the case of spherical symmetry, all the eigenvalues are all the same, okay? Because that's spherical symmetry means that there is no any preferred direction, so the Hessian has all the three values equal. So if all the three values are equal, the ellipticity is 0 and the prolapse is 0. This is a sphere. Otherwise, it's an ellipsoid. Okay. What we want to see is how close we are to a sphere. Okay, that's the idea. Now, so let me use the variable which is the Laplacian, if you want, sum of lambda I call it x. Okay, and so if I call x this variable, then well, basically everything is given in terms of nu. Now my variable is x, e, and p. Okay, so now I'm just changing coordinates, e and p, and I call it alpha, and alpha. Okay, so those are my variables now. Okay, so what do we want to do in peak theory? Then what we want to do is simply count the number of peaks at a random position x. Okay, so the number of peaks at a random position x, it's simply the sum of delta function in x minus x where the peak is. Okay, so that's and then what we can do, we can actually use now the fact that the peak has the first derivative equal to 0. So that means that we can actually expand eta I of x. This was the first derivative. I can also expand the first derivative. This guy is equal to sum over j of psi ij of x minus x at the peak, j. Okay, and if I do that and I take the delta function of this, I can replace the delta function of x minus x con 0 in terms of my variable eta and psi. You see that? I did the delta function of this and the delta function of that. And it turned out to be, I mean, it's very easy to see immediately that x minus x peak is actually equal to the determinant of psi multiplied by delta 3 of eta. Delta 3 of eta makes sense because it's where the peak is, where the first derivative has to be 0. Okay, so the peak is determined by the vanishing of this delta 3, and we have a Jacobian which is related to the second derivative. Okay. Now, what we are interested in then is the mean value of the peak. So the mean value of the peak is nothing else than the integral of the PDF, that is this Gaussian, multi-Gaussian, I wrote it before, some point, of that depends of nu x. I'm going to show you what is exactly the thing, e, p, and alpha, and then mp, right? I want to have the mean value of the peak, so I take the PDF, I multiply by mp, and I'm integrating over, well, the 3 alpha and all the other coordinates, dx, de, dp, dg, so d nu. Okay. Now, yeah, I should put, well, so alpha, I remind you that alpha is simply equal to eta divided by sigma 1. So they are related. Okay, so delta function is related to that. So the integral in the alpha, it's trivial because it's delta function. So it just pick up the 0. Okay, and so now what I can do, I can write down the marginalized probability distribution when I integrate in alpha. So it's just the probability distribution once I know that there is a peak. Okay, so this will be then the PDF
So you're calculating the number of peaks.
the number of peaks.
I mean,
The mean value of the number of peaks for now. Okay, so this is the mean value of number of peaks. So with the constraint that the first derivative is equal to 0. So I take my random variable and I put the constraint that first derivative is equal to 0, and a second constraint I will put that x is bigger than 0.
and there is no threshold here.
No, here I just, not yet. Well, we are not calculating the formation of black hole. We are just asking the following question. If I have a high peak, is this spherical or not? Okay, so we will connect with the threshold. So the threshold, you can already imagine that when I say if I have a high peak, it means I am over threshold. That's what it means. Okay. All right. So then the PDF that we are gonna use now, it's marginalized on nu. So I'm basically integrating on nu. Sorry, it's marginalized on alpha, which is the first derivative. So this is gone. It was just a delta function. And this guy turns out to be, well, some new normalization, x to the 8, e to the minus q nu x, e to the minus q ep, and then j ep, and that's it. Okay. So I could write down, but I don't have much time. So all these things. So this is just a quadratic forms that relates nu and x, e and p, and this is another function that relates e and p. Okay. So what we are gonna do is, what we want to ask is, what is the probability distribution of E and P, so the electricity and prolapse, because we want to know whether the system is spherical, given a value for nu and x. So given if you want a threshold, over threshold, okay, and a value for the curvature. How do I do that? So then this is equal to the so this is Bayes' theorem. So this is the PDF on nu, x, e, and p. Divided by the PDF of nu and x. What does it mean, the PDF of nu and x? Means the probability distribution, this one, integrated in EAP. So I marginalize over EAP. This is Bayes' theorem. Okay, so that's the condition probability. Okay, so this is PDF of nu and x. It's simply the PDF, the integral of PDF of nu, x, e, and p integrated in the dp. Okay, so that's the definition. And so now the thing that you're gonna do, so now you have this conditional probability, and I'm not gonna do the calculation, but what you can do, you can ask which one is the maximum of this probability distribution. Now the maximum of this probability distribution is the value for dE p of E and P given nu and x equal to 0, and dP of P, PDF, E and P given nu and x equal to 0. Okay, so this will give us the maximal probability. Okay, and what we see is that, so if you do this calculation, you will see that a small value for EMP is happen only when x is large. In fact, this goes like e to the minus 2 goes like 5 times x squared. So that means that it's very depict, okay? And p, the prolatelness, is 6 times e to the 4. So it's always much smaller than the ellipticity. And then you ask, okay, but which one is the maximal probability of x, of having a value x? So what you can do, you can take the full probability and take the derivative dx of pdf equal to 0, and you will find that actually x is equal to gamma, which is a coefficient that depends on our correlation function multiplied by nu. So this is the key result. Okay. So whenever nu is large, so the peak is high. The peak is not only high, is also very steep, and immediately our perturbation is spherical. It's close to be spherical. Of course, there's always an approximation, but okay, you see that, no? X large, E goes to 0. And P as a consequence. Okay, so this is the first part of the statistics. So what we just found out is that if nu, which I remind you, nu, it's simply G divided by its correlation, G is much bigger than 1, then our initial configuration is spherical. And because it's spherical, we can use all the compaction function that we have done before. Okay? And this will happen because we are interested in rare case. All right? So we are interested in rare case, so G divided by the variance is much bigger than 1, which immediately implies that, the system is almost spherical, and immediately implies that we can use the compaction function and show the threshold that I calculated before. Okay? So the next step now is to connect this to actually the primordial black hole, because now what we did is only to calculate the mean value of peaks. I can tell you what is the mean value of black holes. Okay? Because even if I have a peak, that doesn't mean it's a black hole. It just means that it's spherical. Okay? So we have to introduce all this part of the statistics that now depends on the compaction function. So while before we were doing the statistic in X, now we have to do the statistic in R. Okay? Because the compaction function threshold depends on R, on the maximum on R. Okay? Once the peak is found, then you just move your radius to find the maximum. Okay? So the idea is the following. Pictorially, it's this. That we take, so if we take some smoothing, our compaction function on our radius, so we move this in space, and we find the value where this bubble is larger. Okay? Once we found the value of this bubble is larger, we also ask which value for the radius of this bubble give me the largest point. Okay? So it's 2 maximums. Okay? And this is where I find the threshold. Okay, so then the new statistics is now the statistics in R on G of R. So it's actually simpler than what we see before. So GR now in X con 0, now I found the peak. Okay, so I have this statistical part, and then I have to combine another statistic, which is what is the probability that G has a maximum and is over threshold. Okay, so this is before we had a statistic in 3 dimensions. Here we have a statistic in 1 dimension because it only depends on R. Okay, so but it's very similar of what we have done before. We have to just use what is called excursion set, which is, I don't have time to explain much, so I want to give you some result. But what we want is the following. So we want to find statistics that has the following, that the gradient of G is equal to 0, and the Laplacian of G is less than 0 to have the peak in space. Then we want to have the derivative in R of G equal to 0 and the second derivative in R of G less than 0 to have the maximum of the compaction function. And third, we want to have that the value of the critical value for the value of G is bigger than a critical value of G that depends, now we know, on this Q. Now this Q, in fact, I will actually rewrite in terms of a new variable W, which is nothing else than what I call the second derivative of G. Okay, instead of taking the second derivative of C, I'm doing the second derivative of G. Okay, but there is a relation, of course, these two things. Okay, so well, so then once I find a peak.
What about the developed earlier, right? Regarding the compaction function and all, talked about a single peak, essentially.
No, it's a collection of peaks. So what happens is that we are counting the number of peaks in space. And for each of these peaks, we ask whether the compaction function is over threshold or not. Okay, so we are considering the mean value of peaks. Okay, so that's peak theory, exactly. So that's in space, here and there are peaks.
No, I understand the later part, but the earlier part, when you wrote a relation between the GR and zeta, for instance.
Yeah.
We always talked about a zeta, which is radial, and so
sure.
Always
around each
I'm
peak,
talking about
right?
One peak in my universe.
You are talking about one peak in your universe, and then you take another peak in the same universe, and of course this is statistically distributed. It's real-time formalism. Okay. Okay. So then now our the statistics. It's well, it has to take all this into account and have to count now the number. If you want, what we want to calculate is the number of black holes now, not the number of peaks. Okay, the mean value of the number of black holes. In fact, what we want to know, it's actually something different. What we want to know is the mean value of the energy density of those black holes. So that's where it enters also the mass function. So, sorry, not the mass function, the mass of the black hole. Okay. So one finds that that basically, so if you do the same thing also introducing the one-dimensional statistics, one finds that omega PBH, which is defined as the mean value of the density of PBH divided by the density at the equality, which is what we are interested in, okay? So this is equal to an integral in all possible smoothing scale. I put it logarithmic. Then the integral from 0 to infinity of all possible curvatures of my compaction function. So omega is simply the second derivative, okay? And then the integral here where it comes the threshold from the critical value of our G at that depends on omega up to 4/3, and this is given by the type 1 black hole of what? Well, of dg of some integrand, okay, that depends on G, W, and R. Now this integrand has a form that I can sketch, and is the following. It's this integrand, it's omega that comes from a Jacobian. The Jacobian on transforming G into derivative of G, so you get this omega. Then you get the mass of the black hole, because we are calculating density that will depend on R, G, and W. Why? Because the threshold depends on W, the compaction function depends on G, and the universe mass depends on R. Okay? And then we have some function which is, well, x divided by sigma x. This is the peak theory function, and this goes like x to the cube. Not gonna. Okay, so let me put a proportionality factor, and then we have the probability distribution. The only probability distribution that left is the probability distribution of join G and W divided by square root of 2 pi sigma square of V, where V is nothing else than Rm, the first derivative of G that has to be equal to 0. So then the leftover of the Gaussian part of V is just the normalization, if you want. Okay? So just in the denominator. Okay, so this looks very complicated, but it can be handled. In fact, it can be handled even analytically. So we have shown in a later paper, you can find the analytical estimation of this in Fumagalli, Garriga, Germani, Chef. And okay, so what happens is well, what we are interested in rather than, so this is the abundance, so it's what we want to have order 1 at equality, but what often we are interested in is the mass function. So the mass function is defined such that omega PBH is equal to the integral of d log all possible masses of the black hole as a function FPBH, so this is the mass function of m dot. Okay, so this means that you give me a mass, I give you how much it's around. Okay, and so you can calculate that, and well, I will not have time to do that, but the way you do, it's basically, because here we have an integral in G, as you can see, so what we can do, we can trade the mass. We can trade the mass of the black hole, which is a function, as we said, in terms of G, W, and R. And what I can do, I can actually write G, I can change coordinates, and I can write G in terms of a function that depends on m dot, R, and W. So simply inverting this, okay? So then instead of having an integral in dg, I'm going to have an integral in dm, and I can extract the mass function. Okay, that's the trick. Okay, so a couple of things that are interesting is the following. That
where is the power spectrum that goes in it?
Oh, the power spectrum is everywhere now. So the power spectrum, it's in the probability distribution PGW, which I wrote it somewhere. Well, I erased. But so this I has a Gaussian distribution of G and W, and there is where the power spectrum enters. Okay, it's the Gaussian and depends on the in the width, exactly. And in fact, so generically what happens is the following, that this is what I want to remark. What we are doing, we are scanning over all possible generation of profile. That means that profile that have a maximum of the compaction function in any point R, and it has any curvature. Okay, so this really scans over all possibility. So you should not generically just pick up one profile. For example, you should not pick up the mean profile, because in certain case, the mean profile, you can calculate, of course, the mean profile that will appear there, but the mean profile in certain case will be good because all the statistic it's just squeezed around the mean profile, or in certain case, the profiles are all spread and you cannot just take one. In fact, this is the case. For example, if you take a power spectrum, so we go now a power spectrum, which is a monochromatic power spectrum, which is A, K0, delta, K minus K0. Here is some peak, okay? Then what happens is that basically all normalized variables are all the same. What does it mean? It means that G divided by sigma G is equal to W divided by sigma W. So this is the value of G, this is the value of the Hessian, and then we have also V divided by sigma V. Now, fun enough, so what we want is that V is equal to 0 because we want to have a maximum, okay? So then you would say, my God, so that means G and W also has to be 0, okay? But we saw yesterday a trick similar in the case of general relativity. In fact, one possibility is V equal to 0, but the other one is sigma V equal to 0 as well, okay? So it so happened that there is a point, there is a radius, which is 2.74 over k naught. In this value here, this sigma z goes to 0, and so even if we are taking v equal to 0, this is a constant. Okay, this ratio is a constant. So for the power spectrum, which is a monochromatic power spectrum, we select 1R. This is a delta function in R. So we are selecting basically a mean profile, Okay, so if we have a monochromatic power spectrum, we are gonna select a mean profile, and the mass spectrum is not gonna be just monochromatic because we have also the scaling law due to the mass. Okay, so the mass spectrum is gonna be something like this, FPBH, in terms of masses. It's gonna be something that grows like the scaling law, m to the 0.36. Then here is the value at k0, okay? And then it's sharply cut off by the exponential suppression of our statistics. Okay, so there is some kind of spreading of the mass. But what is interesting now is to see a broad power spectrum. Okay, because you can imagine that a monochromatic power spectrum is kind of a toy model that is never, is never the reality, let's say. So for a broad power spectrum, things completely change. Because for a broad power spectrum, it so happens that actually there is a huge spread of profiles. Okay, and in fact, that's why our paper we call the unexpected shape of the mass spectrum of the mass function profile, because if you take now a power spectrum that has some amplitude and it's broad, so it goes from some k UV to k infrared. So typically, the power spectrum we saw in the Sriram lecture, that the typical power spectrum of zeta, okay, it's kind of like this for primordial black hole. Goes up and then do this and then goes down. Okay, right? So this is in k. So let me call this k infrared and let me call this k UV. Okay, so if I have broad power spectrum, then I have these to scale. What people thought at the beginning in the past is that, well, the mass that I produce, it should be related to KUV. Why? Because when I calculate the statistics looks like, it seems in what is called Press-Schechter probably, it seems to be dominated by the UV modes. Okay, you can imagine that, you can think that UV mode is a lot of energy, so then the black hole should be there. Okay, but in fact, this is not the case, because what happens is that all these black holes are exponentially unlikely respect to the black hole of infrared masses. So basically, what you're gonna find by following these statistics is the other way around. So if the distance between these two is large enough, you can imagine a kind of a decoupling. So I'm gonna have, for the UV, I'm gonna have the peak that I had before in the monochromatic spectrum, and then I'm gonna have a second peak that is due to the infrared. And it so happened that this is way larger. Okay. So basically, physically, the system is telling you that it's more favorable to form a large black hole given by a sum of very small UV masses that form different, very small black holes, but with the same total mass. Okay, so you can imagine even physically that this is nature would disfavor to form many objects than just one big, and this is actually what happens. Okay, so if you have this thing, it's favorable to form a very large black hole.
Is it simply because those modes re-enter sooner?
Well, they re-enter sooner, but that's not the issue. The issue is really that there is the kind of nonlinear interaction between them. So there is, of course, a dilution of that they enter sooner. That's one way, but it's not only due to the dilution, to the redshift. I mean, it's also due to the fact that really it's statistically improbable to form a very large, more improbable to form a very large overdensity for UV mode than a smaller overdensity for infrared mode, because for infrared mode you will need basically less, a smaller threshold if you want. Okay, so what happens is this. So this is very interesting because it changes completely everything that we think on constraints on primordial black holes. Because if we have a large a power spectrum that is broad, and broad just means that the number of efoldings actually has to be bigger than 3, which is basically always, okay? And but then what we have to check now is that the distance, of course, between k UV and k infrared goes like e to the n, which is the number of efoldings. So we have to be careful no longer to see that this is in the asteroid mass, but that this is in the asteroid mass. Okay? And not only that, we have to be careful that this doesn't enter into the evaporation limits. Because if this enter into evaporation limit, even if it's a smaller peak, we will have a certain number of primordial black hole into the evaporation limit, which can generate radiation and destroy all our prediction of Big Bang nucleosynthesis. Okay? So, as we can see, the morality is that we have to be very careful with the statistic we use, because it may change completely our vision of primordial black holes, okay, in terms of the constraints and the abundance, of course. So, yeah, I think I can stop here, and if you want more details than this, there is a lot, of course. I didn't show you all the calculations, but I hope you had the feeling of what is going on. So the important thing is that you have to do a statistic on the compaction function and not a statistic on the overdensity. And the important thing is that you have constraints, which is the existence of a peak, a large peak, the existence of a maximum for a compaction function, and the fact that the compaction function is over threshold. This will give you a primordial black hole. Once you have a primordial black hole, you can statistically count the number of primordial black holes, and you can statistically calculate the energy density of these peaks. Okay? And this is what we call the abundance. From there, we can calculate the mass spectrum, the mass function, which has this peculiar behavior in the broad spectrum, which is basically the physical case. Okay? Okay, thank you very much.
The ratio of the heights, the ratio of those two heights.
Yes, the ratio there.
Essentially, Ku by Kb.
I tell you, it is e to the 0.56 n.
Okay, understand. That's what I expect.
Yeah, it depends on n, sure.
It should depend on only the ratio.
Yeah.
And this is the latest in terms of understanding?
Latest.
Okay.
Like 1 month ago. Perhaps 2. So I understand it's quite complicated, the whole thing. Okay, so it is quite involved because it goes through statistics, general relativity, nonlinear physics, and all these things. So it's quite difficult to digest. Okay, but I mean, we have to do things properly, because otherwise, you can imagine when you are talking about statistics, you're talking about rare event, you're talking about exponentially lower values, okay? Because we are going to the tail of a Gaussian distribution. So using the wrong ansatz will give you exponentially wrong result. So we are not talking about order 1, we are talking about 10 to the 20. Okay, so it's really important to make the thing correct. And I never talk here about non-Gaussianities. Of course, life is not as easy as this. I mean, non-Gaussianity do probably exist, even if we can measure. But if inflation is our mechanism that generated the universe, then automatically generates non-Gaussianity. Okay? So the whole thing here then would change, and there is actually, this is completely an open question of what happens to the full statistics for non-Gaussianity. So if someone of you wants to have fun, this could be a direction to go, and would really do a good service for the community.
So there is no way either Preschecter or any of the other formalism is going to predict something like that.
For non-Gaussianity?
No, even for.
No, there is not, because in fact, Preschecter. No,
second peak.
no, precisely. All of the other would predict this. That's it. So if you see all the papers so far, you see a peak in UV. You can forget the infrared, everybody say it, and you just get a decaying that actually goes like m to the minus 1/2.
Correct. The location of the peak.
Yeah. And that this is redshift, yes. So this is redshift. This is the mass scaling. It goes like 0.36, redshift and peak. This is what you will find in any other statistics that use only the statistic of other objects, let's say. Okay. So you will completely miss actually the dominant term. Okay, you can see this is changes completely the story, observational at least.
And you're saying even the lower peak, they will emit radiation and they will change the.
Well, it depends where it is. It depends where it is in our plot of constraints. So you know this is the there is a hole here. So if the other peak is here, so you have to be careful. So you have to have that the two peaks are inside the hole. Well, or at least are below any other thing. But the danger thing is that the infrared part is the dominant. That's the danger.
I understand.
Okay, so that brings us to the end of Professor Germani's lecture on modern tactics. We would like to thank him very much.
Thank you very much for staying here. Oh yeah. Thank you very much. Thank you so much.
So I should also mention that Professor Germani will be here for another week. So in case some of you,
Yeah.
at least the ones who are at IIT or CMR, if you want to discuss something,
Yeah, he's just
Sure.
sitting in my
I'll
office.
yes, you can contact Sriram and
All right. Thank you very much for staying here, and enjoy the lunch.